So this podcast is designed to give you the opportunity to practice calculating scalar products in different ways and to give you some feedback on your understanding of how to calculate them. So what I want you to do is to attempt these three sets of questions: to calculate this scalar product for these two vectors, to calculate this scalar product here, which is in 3 dimensions, and then for this setup with vectors A, B and C, and their magnitudes are given here and the angles are shown on the diagram, to calculate these scalar products. And the rest of the podcast contains the answers to the questions, but please do not look at the answers until you have given the questions a good attempt. Otherwise, you really won't get much of a benefit from this podcast. So I hope you enjoy doing the questions, and I think you should now get pen and paper and pause the podcast. Welcome back. Okay, so let's go on to the next slide and look at the first question. So here is the answer to the first question: to calculate the scalar product of these two vectors given in component form like this. And to do this, we recall that if we write our vectors in component form, then the scalar product is very simple to calculate. You take the coefficient of the vector A in the I direction and you multiply it by the coefficient of the vector B also in the I direction, and then you add to it the coefficients in the J direction, those two coefficients multiplied together again. So in our case, the scalar product of A and B is going to be 3 times 4 plus, and then it's 4 times minus 3. And when we expand that, 3 times 4 is 12, 4 times minus 3 is minus 12, so they're going to cancel and the scalar product vanishes. So whenever we get an answer like this, we ought to ask ourselves why. And let's recall the other formula for the scalar product, which is that the scalar product of two vectors is given by the product of the magnitudes, so the magnitude of A times the magnitude of B times the cosine of the angle between the two vectors. Now, we remember that the cosine of 90 degrees vanishes, so this tells us that the scalar product of two orthogonal vectors, vectors separated by an angle of 90 degrees, is going to vanish. So the question is, can we see that these two vectors point in directions such that they are separated by 90 degrees? And I'm going to show that on the next slide. So before I do that, let's just quickly remind ourselves we've used here this key formula for working out a scalar product in Cartesian coordinates i's and j's, and we've also reminded ourselves of this geometric approach to the scalar product, and we're going to use both of these formulae repeatedly in the rest of this podcast. So we want to see, why are these two vectors given here orthogonal? And to do that, I've just drawn here a set of axes, and I've tried roughly to do this to scale by hand. And A is 3 steps in the x direction and 4 steps in the y direction, so it's somewhere around here. And B is a little bit further, it's 4 steps in the x direction and it's minus 3 in the y direction. And you can see that these vectors look, fairly close to being perpendicular to each other, but we can calculate it in the following way. The slope of this line, which I'm calling OA, is 4 steps up divided by 3 steps along, and the slope of OB is minus 3 steps down divided by 4 steps along. And if I take the product of those two slopes, I get 4/3 times minus 3/4, and the 3's cancel, the 4's cancel, and we're left with minus 1. And this tells us that the product of the lines is -1. This tells us that the lines are orthogonal. So if you've got any two lines and you multiply their slopes together and you get -1, it means that the lines are orthogonal. A completely different way to approach doing this would be to calculate this angle, which you can do because you have got A in component form, and also to calculate this angle, which you can do because you have B in component form. Add the two angles together and verify that you get 90 degrees, but I will leave that for you to attempt. So with this, we've seen why the scalar product is 0, and we've reminded ourselves that if we have two vectors at right angles, the scalar product vanishes. So now let's move on to the next question. So in this question, I want to calculate this scalar product here. And we just look at the component in the I direction here. We multiply it by the component in the I direction here. So that's 3 times -2. So we get this is equal to 3 times -2. And then we look in the J direction and we have 4 times 3. So we're going to add to this plus 4 times 3. And then we're going to look in the K direction, these being three-dimensional vectors, and the coefficient here is -2 and the coefficient here is -3. So what we're going to have is plus -2 times -3. So what we have, simplifying, is -6 from here, 3 times -2. From here we're going to get 12. And then finally from here, because it's a negative number multiplied by a negative number, we're going to get a positive result and we're going to get 6. So we're going to get plus 6. And what we see is that the -6 and the +6 will cancel. So they cancel, and this tells us that the result is 12. So we see that 3i plus 4j minus 2k dotted into, but I much prefer the word scalar product because it makes it clear that the answer is going to be a scalar, minus 2i plus 3j minus 3k is equal to 12, and as I say, the scalar product, the answer is a scalar. So with that, I'm going to move on to the next question. So in this final question, I want to calculate these four scalar products, and the vectors are marked here on the graph, and these are at their magnitudes. So let's start off by calculating the scalar product of A dot B, and to do that we're going to recall the following identity. So the scalar product of two vectors A and B is the modulus of A, the magnitude of A, times the modulus or magnitude of B, times the cosine of theta, where theta is the angle between them. So in this particular case here, A is here, B is here, their magnitudes are 5 newtons, I'm taking examples of force vectors, and B is 4 newtons, and the angle between them is marked here as 130 degrees. So what we have is that the scalar product of A and B is 5 times 4 times the cosine of 130 degrees. And it's very important, if you're calculating something like this with a calculator, to ensure that your calculator is set up in degrees, or you will get completely the wrong answer. Similarly, if you're calculating something and you want it to be in radians, you must ensure your calculator is in radians. Now, if we think about the cosine of 0 is 1, the cosine of 1 is 0, and the cosine of 180 degrees is minus 1, so we're expecting this to be somewhere between 0 and minus 1. So the answer is going to be negative. So what we have is 20 times the cosine of 130 degrees, and when we use a calculator, we obtain minus 13, and the units would be newtons squared, because this is newtons times newtons. So that's our first answer, that the scalar product of A and B is minus 13 newtons squared to two significant figures. And now we can just repeat this for the scalar product of B and C. And the magnitudes here of B, it's 4 newtons, C is again 5 newtons, so this is going to be 4 times 5 times the cosine, and now let's look at the angle between these two vectors. It's 130 plus 30 plus 30, so that's going to be 190 degrees, adding it up. And again, that's going to be negative. It's going to be a little bit larger than minus 1, so it would be about minus 0.9. And again, we put this into a calculator, so we have 20 times the cosine of 190 degrees, and we obtain minus 19.7, and to two significant figures, that's minus 20, and again the units would be newtons squared. The third scalar product we had to calculate is done very much in the same way, and we look at this now and we see that the angle now is less than 90 degrees, the angle is 60 degrees, so we expect this scalar product to be positive. The modulus of each of the vectors is 5 newtons, so this is going to be 5 times 5 times the cosine of 60 degrees, and so that's 25 times the cosine of 60 degrees, and the cosine of 60 degrees I happen to know is a half, so that's going to be 12.5, or to two significant figures, 13 newtons squared. The fourth exercise was to calculate the scalar product of the vector form by adding A and B with C, and all we have to do is expand the brackets, and we say that this is the scalar product of A and C plus the scalar product of B and C. And we have calculated both of these two vectors, or these two, scalar products already. So A dot C is approximately 13, B dot C is minus 20, so it's going to be roughly minus 7. But what we should do, if we want to work this out to two significant figures, is retain more significant figures here and here for the sum, because there is a cancellation taking place here, and that can introduce significant rounding errors. So I go back to this value and this value, put them into a calculator, and we are going to obtain minus 7.2 newtons squared. So with that, we've come to the end of this podcast, and in it we've used this geometric formula. We've also used the formula in terms of Cartesian coordinates for calculating scalar products. Both of the formulae give the same result. And in case you were wondering, by the way, when I calculated, for example, the scalar product of these two vectors, why we use this angle and not this, well, you can use both and they will give the same result, and you can show that using properties of the trigonometric functions. I hope this has helped you improve your mastery of scalar products, and I will stop this podcast now.